warm. You warm, you have your hat on.
Oh, yeah.
Yeah. I mean, it's supposed to be 72 today. It's supposed to be like summer today.
During the spring, I don't know, I have a kind of allergy to the, especially in the morning.
Oh, allergies?
Yeah.
Yeah.
So when my head, yeah. And so,
All right.
I know it's weird.
No, it's just kind of like today's a weird, you don't usually wear it, but today is like going to be a warm day. I'm planning for summertime today. Yeah. Yeah. I don't know. It rained a lot this morning. I mean, with thunder and everything, but that should clear the air for allergies, I guess. I'm not sure. It's today, it's kind of weird. Like there wasn't any traffic coming in at all. It's like, is it yesterday was opening day downtown. I guess people got drunk. There's like a big, like my wife does she ushers at the plays and things. So she went downtown yesterday. And I guess it was like there were stabbings and stuff. Like a lot of stuff was going on. Like it was really pretty crazy. So anyway, there's a parade, for the baseball. They the Cincinnati, I think it's the first game of the season for the entire country or something. So they have a huge party downtown.
Not anymore, but it used to be.
Yeah. Well, anyway, I guess yesterday was pretty crazy, like up until at night, but anyway, I'm gonna get started. So yeah, for some reason, that's why I think maybe there's not many people today or something. But anyway, all right. So this stuff, this is pretty difficult paper. So anyway, there's kind of two papers here. Okay. So there's like a relatively simpler paper, this Tas Tassapatsaris. Sounds like Greek. And then this Kamani, is Kamani Iranian or?
I think the name is more like India, not from India.
Oh, India. Okay, yeah. All right. Well, there's some interlope between the versions, I guess, somehow got to India. Got mixed up. I mean, Afghanistan is Persian, right? And then Pakistan's the next country in India, so maybe some northwest India or something, I guess. Anyway. So anyway, so this two papers, it says to like compare. First, the homework is like to compare these two. So I thought I'd just quickly go through this one, which is the same thing. So Yavik worked with Tad Koga. He's a Japanese guy and teaches at Stony Brook, who's been there for a while. I think he worked with Hashimoto in Japan, who's like the guy, like a neutron scattering, pretty famous guy. And then Tessa Passaris, and Lutz Weigert is the guy that runs the XPCS at Brookhaven. Then these other people, I think, are mostly from this adhesive, this Henkel epoxy company, which is a German company in Dusseldorf, but they have a research lab in Bridgewater, New Jersey, which is how they connect together, right? So they're looking at curing of epoxy. So it's the same thing that that Yavit talked about. It's basically the same study done on a different system. So, all right, so the weird thing is that, so they show, this is a normal scattering log-log plot, and you're kind of looking for particulates. So you're looking for a power 4 here. So you go like 1, 2, 3, 4, and 1 decade. So you're looking for that kind of slope. That would be the surface of particles, -4 slope. There's nothing like that in the data. And the data, in fact, is kind of like 2, kind of like a 2 slope. And he says 3.2 over here. So it's a little bit shallower here and steeper here. And it's got these oscillations. So this data doesn't make any sense because he says the material is composed of mica, which is large, he says, beyond the range he's looking at, and then fumed silica, which is, fumed silica is going to be like, and both papers are looking at fumed silica. Okay, so See if this works. Is this right here? Yeah. This is about kind of right. So fume silica is like this, right? Aggregate of things. And the typical scattering pattern is like that 1.8 and then -4 like that. And this is the size of those particles is here. This is log intensity log Q. That's the size of these small particles, and that's the size of these aggregates. That's the kind of thing you're looking for. That's what it looks like if it's just fume silica. And both papers look at fume silica, right? So no peak because they're polydispersed particles. They aren't. So if you colloidal silica is like spheres, perfect size. And when you look at that, you get a -4 to the surface, but superimposed on it will be like oscillations that have to do with this perfect size. So this like 2 pi over that Q value is going to give you like the diameter of the spheres. Right, so that's perfect spheres. Fume silica is made in an explosion, so it's not perfect spheres. This is made in a solution chemistry. We use surfactants to make it, right? So it's perfect. Anyway, so that said, this scattering pattern makes absolutely no sense. It doesn't, I would have shoved that scattering pattern into the supplemental because it just said we're measuring XPCS. We don't care about what the structure is. So you can see he uses a polydispersed sphere function here to say that's what that is, but the stuff isn't. Anyway, this is pretty messed up. So whatever it is he's looking at, he doesn't know what it is. So that's kind of, it's got contrast. We get to XPCS measurement. He can measure the dynamics as the epoxy cures. And that's kind of what he's looking at. Because I think it's only like 2 to 5% of the silica in it. So it isn't even above the overlap concentration. So the silica isn't even networked. It's just kind of a viscosity enhancer. It's just making the viscosity go up a little bit, right? So it's not really a functional reinforcing agent here. It would have to make a network of filler to be reinforcing. Anyway, so he's looking at, but it does have mobility because it's independent. So basically, he's looking at the mobility of those particles as it cures. And then he shows, so normally, so in Yavit's stuff, this is reversed. So this is T2 and T1 for the correlation function. So again, let me just go back here. The memory on this. You're measuring, you have your sample, and then you're measuring at some angle, which reverts to Q. So 2 pi over the size that you're looking at is kind of related to that angle. It's 4 pi over lambda sine of the angle by 2 is going to be Q, and that's 2 pi over the size. Just looking at some size scale. So you pick up the intensity here, that intensity at that Q, that magic Q versus time has an average value, and it fluctuates because these particles are kind of moving around inside the thing. So whatever the structure is of that scattering curve, it should look like this, and actually looks like this. Whatever that is, he's looking at it move around, and this fluctuation has to do with that thing moving around, whatever it is. And as he cures it, it slows down. Okay, so it should be, if you do a correlation function of that at time 1, you have like time 1, and then time 2, and then you got to vary time 1, time 2. So the dot product of those two, the average over the average of the I squared, gives you this correlation function. That thing should go from 1. So if the T1 equals to T2, it's perfectly correlated, and this thing is I squared, so it equals 1. If it gets decorrelated, this thing goes to 0 because it's random plus minus. It'll go to 0. So this thing will be like the exponential decay T over tau. You get this relaxation time from that. So as it cures, the relaxation time should get larger. You should get, so initially, if it's moving fast, this should be a quick relaxation. As time goes on, as it cures, it should slow down, it should broaden out. Right, so because of a time changing system, he plots T2 and T1, and he's going to plot this correlation function as a color scheme of this thing. And as it cures, it should be moving fast at the beginning, so very narrow. Then it should broaden out as it goes. And this line is where T1 equals T2, so that's perfectly correlated. So that should be the darkest. Then it should decay down exponentially away from that, like that. Okay, so if you can follow that, so there's a time of the measurement, time of T age, they call in the other paper, is T1 plus T2 over 2. When you're in the middle, T1 equals T2, so that's just T age, the time. So as you move up this way, it's just as you cure the sample. That's curing the sample. Then you're also kind of curing off in the diagonals. Basically, if you take one that's like this, that's where T1 plus T2 is constant. Right? If you have a diagonal line like this, like at this point, that's T age. At that point, that's T age. And in between, you're kind of at the average of T1, T2 is T age. So if you go sideways on this, you get the decay curves like these for a given period of curing your epoxy. Right. So that's kind of what Yavit was supposed to say, I guess. And so you should, but here, this thing has a backwards problem. So it's like it doesn't broaden out as it goes up, it gets narrower. And that's because this isn't at a single temperature. So his measurement is, what he's doing is he's heating it up. He starts at 40 and goes to 80. So at 40, it's moving slower, and when he goes to 80, it moves faster. So it's a little bit more complicated. This is a realistic epoxy curing scheme for microelectronics. So it's going to be applied at 40 and then put into an oven at 80. Then they take it out. So they're going through the actual regime of making electronic packaging, right? So, right. So that's why this thing looks like that. And then this one kind of broadens out. So that means that the decay time gets longer as the thing cures because the viscosity gets higher. So relaxation time gets longer. It slows down as it makes a network and makes a solid. And this goes up to 300. So this is kind of normal stuff. It's a little bit twisty because he's doing this curing thing. So it's a little bit more complicated than the other papers. And also the other thing he does here is that so he gets this the other thing he does is he uses a stretched exponential instead of so he uses this equation. So this isn't in the other paper, but so he has e to the minus kind of t over tau. So gamma is a rate, it's 1 over t. It's like the velocity almost, but so 1 over t. So this is a rate instead of saying tau, and he uses tau for the delta t. But then it isn't just that. He puts a gamma in here, which makes it what they call a stretched exponential. It's like when you can't fit that curve, so you put in a power, and then you can fumble about what the power means. So the power should be 1. And what does he get? He gets some kind of scatter plot for it. Like he gets something near 1. Let's see here. So this is his gamma. It should be 1. If it's just a normal decay, it's higher than 1. And he says that's because it's a so he says 1 would be for a Brownian motion, and then, all right, so, and then he says this is super hyper diffusive, and this would be hypo diffusive, above and below. And this is into mysticism. Like, I don't think you can exactly understand where this is kind of a fudge number that people use, and trying to put meaning into it is a little bit ridiculous. But basically that's what he's doing. And also, if he had a definite value, then you could kind of argue some kind of bogus meaning to it. But since it's a scatter plot, then even the bogus meaning has no meaning, right? So, but all right. So what does that mean? I mean, he's talking about diffusive and Brownian motions. He's saying it would be 1 if it was Brownian. So Brownian motion, you have the mean squared path. Sorry. Yeah. All right. You have the mean squared path is 2 times the diffusion coefficient times time, right? So that means, and if you're measuring Q is like 1 over X. So basically, you'd think that you'd have Q to the minus 2 should go with time, which means that you could plot tau, and time here is tau or delta t for our measurement. So you plot tau versus Q squared. And then as you go to larger size, the tau gets smaller, because you have faster motion. So go like that. That would be diffusive. If you have ballistic, so that's Brownian. or diffusive. If you have ballistic, then you shoot a bullet and it just goes. So it's got a velocity times time gives you the distance. So then you'd expect that the time would go with Q, just straight Q, and it would also, let's see, the position Q's 1/size, so it also decays like that. So it'd be a straight line. So this would be subdiffusive. This is called subdiffusive. And this is diffusive. And this is ballistic and Brownian. So it's kind of like you have case 1, case 2. All right, so that said, it depends on, so in actuality, you shoot the beam at the sample, right? So you have kind of a hole that you're looking at, a spot you're looking at on the sample, and you're looking at little flies flying by, right? So basically, Brownian motion that is based on the motion of gas atoms or colloidal particles of dust in the air. The idea is that they move and then they hit something else and they bounce off and they go on a path like that. That's a random walk, right? So this is where the idea of like the persistence length and the Kuhn length came from, right? Originally. So basically there's a straight step and then it's going to make this squiggly walk in the end, like random walk. Yeah.
So what's the difference between diffusion and self-diffusion?
Diffusion is going to be that the position, the distance that you travel is going to go with time to the 1/2. If this number is smaller than 1/2, then it's subdiffusion.
I mean, physically, like, they will travel less distance like that.
Yeah, it would travel less distance. Yeah, and super diffusion would be like that thing's bigger than 1/2. So subdiffusive motion they talk about. So anyway, all right, so you get this idea. So let's say you're looking at motion of these aggregates, which they don't actually see, but basically you're looking at those things move. Well, and they're following Brownian motion. Well, they have a mean free path, just like a gas atom would, if they're subject to diffusion. So that means that if you look at a small enough spot, so if I look at a size smaller than the density of the particles in a system, in other words, my size, say here, d cubed is less than 1/ρ or something, like the density of the system, right? So in other words, I don't have enough particles to make it change course within that path. So then all I see is ballistic motion, even though it's diffusive. So there's an issue of the size of the beam, because the motion you're looking at is on micron size, and the beam size is 100 micron. So it could be 10, 50, 100 micron mean free path particle. Then you just see ballistic motion, even if it was diffusive. So it's kind of a, yeah.
So what you're saying is the field of view that we're looking at this is too small.
Yeah.
So instead of seeing the zigzag motion, we're only seeing part of a straight line.
Right. Or it could actually be ballistic motion because it's inside a kind of a rubbery gel, and basically there's residual stress in it that are pulling the particles in a straight line. So as it relaxes. So you could be looking at the relaxation of a gel, or your size could just, your beam size could just be smaller than the mean free path of a particle. You don't know which, you know.
Right. So the idea is the beam's too small for us to tell.
Right. Yeah.
Okay.
That's one of the two cases. Yeah. The case they're arguing is that the gel is drying, like curing or something. There's residual stress. It's pulling the things. Any kind of force that you put on it's going to be. Brownian motion relies on KT, which acts in all directions, so it's random. But anything else that you put on it is going to be directional. Residual stress will be directional. So anyway, there's a lot to it. You know, you can see that it's kind of like you could spend a lot of time fluffing around this stuff, you know, and not get anywhere. But in the end, there's a speed. They get a velocity, and they get plots of that velocity, the rate, the gamma. All right, then they get a straight line with Q, which means that it's ballistic. It means it's just got a velocity. The slope of this is going to be the velocity of the particle, and it changes as you cure it. So that's good. Then they can just plot the velocity as a function of the time of aging through their cure cycle. They heat it to 80, cool it down. They can see the velocity changes. if it's a straight line, that means you just have acceleration. Like straight line means velocity is proportional to time. The change in velocity is proportional to time means that's just acceleration. It's got a constant acceleration. If it's different than that, it isn't a constant acceleration, right? It's something else. I don't know. This is a curing thing, so it's more complicated. So initially they just get acceleration or deceleration if particles are slowing down, the time with aging time, and then anyway, so you can, that's kind of the scheme of this, but yeah.
After
The yellow is, the orange is at 80 and the blue is at 40, I guess, according to the plot. So that means the higher temperature is faster. It's got a higher velocity.
after a point, before that, the orange dot is above the blue dots,
Yeah.
and after the point, the orange.
Oh, well, they quenched the system. So this is the temperature here, the orange. The temperature's here, it's orange. So they quench it, right? The blue is, it's just constant 40. The orange, it heats to 80 and they cool it down to room temperatures. That's a cure cycle. So doing two different cure cycles. And once it gets to here, like I think the temperature is kind of, I don't know, who knows? It's epoxy, I mean, in the end, but it's interesting kind of what they did, but basically there's some limitations. And a major one of the problems is that this is not like scattering curve from fumed silica, that this is absolutely not a scattering curve from fumed silica. It's got nothing to do with it. So what they're looking at, they don't have any idea what it is. They're using an industrial, it's got mica in it, it's got a lot of things in it. And I'd imagine there's some things that they don't even know because it's a commercial system. So they're not going to tell them, oh, we put in colloidal silica, spherical particles, because it makes it into super epoxy. But we don't want the Cabot or somebody to know that that makes super epoxy. So it could be that, so something like colloidal silica in it. That's what that looks like. That's the only way you'd get like a cheap material that like Ludox, it's a cheap material you can just throw into anything. I mean, they put it into like drying agents. I mean, it's all over the place. This colloidal silica is cheap. I mean, so it's basically, that's probably what it is. Yeah.
Is there a reason why you quench the system?
Because that's a processing to make epoxy. It's an industrial process for making microelectronics. Like they're going to package the electronics in epoxy. So they're just going through the cycle and they're showing that like, it's a pretty good journal, but I don't, anyway, so I just wanted to show this one because it's a simple one. This is like a simple case of this XPCS, it's kind of similar to what Yavit did, the same group actually. This is a paper we need to look at though. So let's see, get some notes here. That cover whatever I had in mind. All right, so yeah, so we got yeah, you got these parameters that you're looking at. You have the size of the beam. That's going to decide actually whether you see ballistic or diffusive if your mean free path of the particles is bigger than that beam size, which is likely for these kind of systems. Then you have the scattering vector. So the Q decides the size of the thing that you're looking at that's moving. So you pick an angle that decides the size scale that you're kind of observing, right? So of the thing that you're looking at and also of the scale that you're kind of probing to see the motion. So you end up plotting the delta T versus you're going to end up plotting the tau versus Q because that's the size scale where the motion is observed over. So there's a size scale of the beam and there's also the size scale that you're observing. So there's two size scales involved in the thing. Then delta T is this kind of correlation function thing, which is, he calls T aging in this paper, T age, it's T2 minus T1. The T age is a time, actual time of the experiment because of the time changing measurement. That's T2 plus T1 divided by 2. And then tau in this paper is T2 minus T1, the correlation function time, the e to the minus T over tau thing. So, and then, let's see what else. And then, all right, so there's also a tau range that you can look at in the measurement that's determined partly by the instrument. So the instrument's taking pictures like pop, 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 pop. That kind of, I think it's taken it at 20 milliseconds. So the shortest time, the tau that you could measure is 20 milliseconds, right? And then the longest tau that you could measure is like how long you have beam time, which is going to be basically in the thousands of seconds. So there's limitations to what you can resolve because of the cost of the machine and because of the analytics of the machine and the analytics of the synchrotron. Right, and the synchrotron has particles moving around the thing, and that it isn't actually a constant source because if there's bunches of particles flying around, they have a pulse to it on a picosecond time scale. So there is limitations to the timing of it. There's the measurements you could do. And then the ballistic diffusive I already talked about. That covers those two things. All right, so then he's all right. So in this measurement, he's doing this. He's going to put in a rheometer into the machine, and he's got two kinds of rheometers. He's got a cone and plate rheometer, which is a normal thing, and he's looking at large amplitude oscillatory shear. Normal one is small amplitude oscillatory shear. Okay, so that means how fast are you going to wiggle this thing, or how big of a percentage are you going to turn this thing? So he starts out at 0.1% and he goes up to 10%. So 0.1% is small amplitude oscillatory shear. And then kind of when you get to say 0.5%, that's large amplitude oscillatory shear. Because what he's looking at is ketchup, and he wants to see the ketchup come out of the bottle. And when it just hangs there, he's a small amplitude oscillatory shear that doesn't come out of the bottle. When he gets to 10%, it pops out onto his hamburger. All right, so he wants to kind of see that transition. So he's going to go through this with this oscillatory measurement. So he has this machine where he does most of his rheology. Then he has a Couette viscometer, which is a cup and bob viscometer. So he's got this kind of thing. This thing in the middle is wiggling. He makes the whole thing out of something like beryllium, which is kind of toxic metal, especially if you machine it. Machining the powder from this, like, supposedly causes cancer. And he's going to take the X-ray beam and blast straight through the middle of this thing. Okay, so it's a viscometer that was designed to use in an X-ray. So if you look from the top of this thing, it's going that way, and over here it's going that way, and he's going back and forth. So this is kind of a weird thing if you think about it. It's kind of hard to see exactly what's going on, and it isn't. So his pattern is going to have like the shear direction, and then not the shear direction. So it's not, you don't expect to see. So you expect, and the pattern is 90 degrees. So because you're going at a reflection, so you end up with the structures here, but you're looking at something 90 degrees to it. So basically his pattern is going to show up on his detector over here and not here. Everything's rotated 90 degrees, you're looking at a reflection. Right? So anyway, so that said, it's kind of complicated. And he doesn't exactly say like that he's taking like sector, but he must be taking sectors of this thing like that to look at this flow. Right. So anyway, so that's the setup he's using. So then what's the frequency, right? That was what they asked Dan Rather, right? He got mugged in New York City, and the guy said, what's the I don't know if you guys ever heard of that, or if you know who Dan Rather is, but at one time he was a famous person who got mugged in New York. And the question was, what's the frequency? What's the frequency, Dan? So anyway, so he's looking at 0.1 rad per second up to 10 rad per second, which isn't something people normally deal with. And 1 rad per second is the main thing he uses, and that's 6 seconds per oscillation. I guess this one's 0.6. Let's see, 10 is 0.6, and this one's 60. So if you're doing 0.1 rad per second, in 1 minute, it does 1 oscillation. So that's like ketchup in a bottle, right? And when you get to 0.6 seconds per oscillation, then it flows out. It comes out of the thing, right? So this is kind of important to keep a picture of like what's going on. It's so slow, right? It's oscillatory shear, but it's like nothing like this vibrational thing. That's why you can get away with straining at 10% and it doesn't like blow up or something. So anyway, this is that business. What else is here? So then he's going to end up with this plot down here somewhere, this thing. So you can vary the frequency 0.1 to 10 rad per second, which is whatever I said, 60 seconds per oscillation, 6 seconds per oscillation, 0.6, right? And he sees G prime, G double prime. This is done at a low, this is done at like 0.01 strain or something like that, right? So all he sees is that it's gelled, like G prime is bigger than G double prime. It's like jello, right? It doesn't flow. It's ketchup in the bottle before you whack it. Then he decides 0.1 is a good one. So 6 seconds per oscillation. And he's going to vary the strain amplitude from 0.01, which is like nothing, right, up to 10, which is somewhat quite a bit, enough to get the ketchup out. Apparently, like 1% is enough to get the ketchup out of the bottle because that's where it starts to flow. Starts to flow because G double prime is bigger than G prime. So the loss part, the flow part's bigger than that means the liquid over here. And then there's a yield point. So the fluid has a yield point that's a peak in this curve, and that's where the fluid starts to flow. That's where the ketchup comes out. And before that, it's just like jello that wiggles when you whack it, right? So it's got a wiggling component and it's got a Hookean component, right? And both in all cases, but basically, all right. So, so that's part of this thing. Then he's got his model. So the model kind of has nothing to do with it, in a sense. All right, so he wrote a paper where he came up with this. All right, he has a problem with this memory function that we talked about. So he mentions a memory function. He does it in a little bit of a different way, but basically it's the same idea. You whack it, and then you integrate over time and get the memory of the thing. So this memory function decides like how the response to the system is going to be. Just like the response function, more or less. The twist he has, so in the yielding fluid, he has to have a yield stress, so he has to kind of figure out how this works. So he comes up with a theory. So this is kind of like this year, and this theory thing is 2021's like 3 years ago or something, 3 or 4 years ago. Right. So the same guy, Kamani. So Kamani, anyway. Kamani, this thing is funded by a career grant, which is something early, like an assistant professor gets, it's like a special thing, whatever. So it's a 5-year grant. So anyway, so I think it was on this yield stress fluids. And then, so he's got this idea that's different than the memory function. He's got the idea that there's like you put a strain on the material and there's a recoverable strain and unrecoverable strain. And he can measure that by doing this little ditty. So he's measuring the modulus, the storage and loss modulus, the same curve in the other paper, right? And his model is a fit to it, which works pretty good. And then he says of the loss modulus, there's a recoverable part of it, which is a solid part, and there's a non-recoverable part, which is a fluid part. So this gets a little confusing because the loss is essentially the non-recoverable part of the total modulus. So he's breaking that loss part into these two so they can talk about these stress yielding fluids. It's a little bit mushy here, but anyway, so if you have stress and strain, right, and then if it's a Hookean elastic, it's a straight line, and as you apply the stress and relieve the stress, it goes back and forth on the straight line. There's no hysteresis. So when you have this kind of loop, it means there's a loss involved. So basically, if it's a fluid, then you get this kind of hysteresis to the stress strain curve, and the area in this, if you take the maximum stress and the maximum strain, that would be like an area here, and that would be an energy. And if you take the area within the hysteresis loop and that divided by the other is the percent of the total, say, loss modulus that's fluid. So if you can do these measurements in this stretch and release kind of operation, and then get the area in this, he can get the relative components of this loss curve that are fluid and solid, or recoverable and non-recoverable with solid and non-recoverable for fluid. And then he can just break up that curve into 2 parts. Once he does that, so that's possible to do. Then he just says that his total shear rate is a recoverable shear rate plus an unrecoverable shear rate. And then he can break up his Newtonian fluid equation into the stress is the viscosity times the strain rate. So that's the Newton's, that's Newtonian fluid equation. And then instead of the, so his viscosities, so viscosity would be stress over strain rate normally. So he puts in yield stress and then the average strain rate. And then he has this other function. So this would be the recoverable. This would be the recoverable, and that's the non. So normal one is the non-recoverable, or the fluid one, and this is the solid one. So he comes up with this scheme, whatever. This looks like a power law fluid, which these things are. So basically, it's complicated, but basically this is a viscosity. This is a modified strain rate that includes like, so this ratio would be like a relaxation time, like viscosities over modulus is a time relaxation time times a strain rate. So he's got a memory here kind of. Then he also has another memory function over here for this rate of stress, right? So it's a little complicated, but it's basically Newton's law with a bunch of fudge things in it. And he ends up with parameters for this. So the parameters he has, the gamma depends on N and K, and this yield stress, and this viscosity S is one of the parameters, but he can measure those. I'm not sure if it's in this paper or the other one. I think it's in the other paper. So he just, this paper is like an extension of that. He has this. Then he says he can get so the elastic parts, like the modulus, he gets at this low end over here. And the viscosity he gets at the low end. And then from the slope here, he gets this power N. And then the K also comes from that part. So the K and the N and the yield stress comes exactly from that point where he has a peak. So he has a stress at the peak. That's his yield stress. So all these parameters he can get from that plot. And then again, he can kind of, again, this has nothing to do with the paper really, except that he wants to force fit it into the thing. He can get these kind of fits to it, which aren't that great. But, I mean, they're kind of okay. They roughly have the shape, right? But yeah. The K is a constant. All those four parameters are constants. He gets all those four from this, basically from this plot. Say that again. Yeah, he gets the, we understand what you said. He gets from the, let's see, where is this thing? Here, this thing. So yeah, this is where he's getting so he's got the recoverable, fluid would be non-recoverable, solids recoverable. So he gets those two things. Yeah, he gets those two things from this kind of plot, like a hysteresis plot of the measurement. It isn't that important, but basically depends how interested you are in this subject, but basically he can measure those recoverable and non-recoverable strain rates through his measurement. I mean, he's convinced himself that he can. And he seems to be able to predict the function that he gets for the catch-up. So that's good, And I mean, I don't know how many people are going to argue the point, it isn't right or something, but I mean, it seems to be kind of reasonable. Basically what he's done is he presents the memory function and he kind of gives up on it and goes to this other thing, like his own invention, which deals with this idea that you can break apart the loss modulus into these components and end up with a function that could predict the stress yield behavior. So it's a little complicated, but roughly seems to be okay, what he's doing. Anyway, so yeah.
Is the gamma with two dots the second derivative?
Yeah. So that's the rate. That's like the acceleration of this shear. So if you're going through this oscillatory shear, there's a shear rate, but it's kind of oscillating, I guess, in the thing. I don't know. I don't exactly know. Actually, it's pretty weird. You're right, because this has a single, that's got a changing shear rate. So there is an acceleration component to the shear. If you're doing an oscillatory measurement, it's true, which is usually just ignored. Because you just usually take like the Cox-Mertz rules, you can take the frequency and that's the shear rate. But actually there is an acceleration part that maybe you'd want to consider, and he has. So I think normally you just say that oscillatory frequency is the shear rate. Actually, it stops at some point and turns around and goes the other way. So that it isn't really constant. Anyway, so you can see that this could be something that you could spend a lot of time messing around with, like basically, and people have spent a lot of time, and because it's directly important to like paint, like when you put paint on the wall, you want to have something like ketchup that sticks there, but you can make it flow when you put a force on it. Right, so paint, this is really important to like, what's the company in Cleveland? Does Sherwin-Williams, like they love this stuff. Like they would like hire this guy to look at different kinds of paint and glue and whatever. Right, so there's plenty of people that want to see goo. Procter and Gamble, I mean, so it depends what makes you excited. I think it's interesting and all. So they stick that into the XPCS and then they get this thing. Okay, so they're oscillating this guy. So they get a hatch pattern, which looks pretty weird. So they don't oscillate here. So that's their stop. They haven't done anything yet down here. So before time of like, this is seconds, that's like 8 seconds. They haven't done anything. Then they turn the thing on, and then it's oscillating. Each one of these peaks is when they've sheared the thing back and forth. So then you have to say, so probably they first just got that pattern, then they figured out like what's going on. Okay, so this is a correlation. So black means there's that the correlation is 100%, like it's perfectly correlated. So when T1 equals T2, it's perfectly correlated. That's along this line here, right? And then you go to the cross pattern, and then you say when T1. So if you get to so let's see, it'd be better to look at this. Let's see, someplace he shows oscillations in this thing. Let's see if I can remember. Three, four. All right, so I'm wondering if I can do this. So this thing doesn't go to, oh, that one does. This one goes to just the time. So here he's plotting T is the time of the whole cycle. So oscillation with a time period of T. All right, so if this goes to 1, that's one full oscillation cycle. And this guy's also going to 1. And the other plot, it goes to 0.5. That's the one. This one goes to 0.5 because the oscillation cycle is like mirrors itself. So this thing like repeats itself over and over in space. So 0 means T1 equals T2. It's perfectly correlated. When you get to the halfway point, let's see if I can draw this. Definitely have an idea how this worked. It works in my mind, but right now I'm kind of wondering. So he's going through this oscillatory thing going on. And he's got his response. So you have the strain he's applying and the stress that's coming out. Like that. And he's only going to, so this is T and this is T by 2. So he's only going to T by 2 in the cycle because this mirrors T by 2. And he's going to take 2 points in this thing. So he's going to take like T1 and he's going to take T2. So when T1 equals T2, it's perfectly correlated. But also when T2 is here, those two are correlated. So when T1 plus T2 equals, let's see, how does that work? T1 plus T2 equals T or something like that. Then you get another correlation. So that's like a straight line diagonal across. When T1, T2 equals T, then you have like those two, T by 4 or something, I guess, because T's here, 2, 4. I think it has to be T by 4. Then you have the two opposite sides of that half thing that match up. And at that point, those two things are correlated. They're the same thing because it can't tell if it's upside down or right side up. So basically, those two are the same. They're correlated with each other. If it's a Hookean elastic where the strain and the stress match each other. That's the idea. All right, I convinced myself. So that means you get a diagonal where this thing's exactly, and that would happen when T equals 50% of the cycle, then you reach this point where the things match. If it's a Hookean elastic, which it is at the, so this part is pure elastic and this part's pure fluid. And this part, the yield point is is where the two miss the most, right? So at this point, that point where the this is looking at the shift of the strain with respect to the stress. So it's shifted by 90 degrees when you get to a fluid. And it's shifted by like 45 degrees when you have this yield point of the thing. From this, right? And then here it's zero shift. So this is where T1 plus T2 equals half of T, half of the cycle. Then you return back to the same thing. So it's correlated. This is my understanding of it. I'm not sure if that makes sense to you, but basically you have to kind of look at the plots and figure out T1 plus T2 equals some number. And that number at 50%, that means that they're perfectly correlated. That's why they get the hatch pattern. And the reason the hatch pattern shifts is because the stress and the strain are shifting. There's a del between the frequencies of the things. There's a loss in the material, and the loss becomes, you know,
This correlated like the fluid phase.
it's like,
Gel like
yeah, the gel is this, he's looking at solid.
the solid phase.
Yeah.
So the reason why it shifts is because it's changing.
Yeah, because you're getting loss.
Yeah.
So that the stress and the strain aren't in phase anymore. They shift by a certain percent. And then you're getting, basically at that point, you're getting the shift in that curve that has to do with the loss of the thing. It's kind of interesting that you can see it in XPCS measurement. I mean, but so that's the XPCS measurement over here. And all right, so it falls apart a little bit, but basically that theme is there. This is what his KDR model predicts, right? And this is what the rheology measurement shows. So you can do this same correlation function with the rheology measurement, with his KDR model, and with the XPCS. It would have been enough to just compare the measurement with the XPCS, but he's got his model there and it matches up to. It's pretty complicated. I'm not sure. I mean, you could say he's proving that his model works in a sense. I mean, for these kind of yielding fluids, but it's also like he's just kind of doing a show of what you could do with this stuff. So the others are all kind of explaining that the same way. Like he has his T/4, how this thing works, you know, kind of what I said. That shows his Couette viscometer, how he shoots a beam through it. It's a little bit too involved to really criticize this paper, you know, because it's like, it's too deep into it in a sense, and it's into his specific view of the world. So he's got to have a narrow focus. It's good, he has a narrow focus, and he's trying to push this theory, this model he has along. So, anyway, it's of use, you know, maybe to catch up and paint and things. I mean, it's kind of funny. Anyway, it's a complicated paper, actually. Then he goes back and he matches up the amplitude. So he can calculate the strain amplitude from his measurement. Then he has the amplitude of the rheology and XPCS, and everything matches up well. Like he shows that the XPCS and the rheology match each other in that plot, and also in terms of whatever, this is normalized amplitude averaged over n cycles. So this is for one cycle, and this is for averaging. So he's going back to this grid, like the actual data, the actual data is this mega grid thing, and he's kind of averaging over all the cycles of this thing to get this last plot. So he's kind of milked everything you can milk out of this, I think, in a sense, you know. Let's see, before I leave it, all right. So the questions here. So there's questions, I think. Got them again. Oh, there. All right. So response, this is from the class. Unfortunately, I didn't record the class last time, I think. I didn't check, but I'm pretty sure I didn't. So I kind of went over a little bit of memory function. So the response to the memory function, he says in the paper, related by a derivative. The derivative of the response function is a memory function. He explains that kind of in the beginning of the paper. Boltzmann superposition is what he's doing at the start here. not this. It's this business where he does the integral of this, of the memory function. Whatever that is. Not that. This thing, stress is the integral memory function and the strain business. So you add in these kind of exponential decays together to get the response of the system. Which of these models? Oh, and this is from the class last time, the Hookean elastic Newtonian fluid, the birelaxer. Hopefully you can figure that out from the notes of let's see, from the notes of the notes are the polymer dynamics notes, these things. So that after these slides numbered by any chance? Yeah. So slide, this is the Boltzmann superposition. Then again, let's see. Here, that's what I need. Let's go to using the mouse. Here. This is like the classic thing. This is a damped harmonic. So someone asked like over damped and under damped. So harmonic wouldn't be decaying. And if it's over damped, it's this curve. And if it's under damped, not sure about, this is over damped harmonic. Anyway, that's a damped harmonic. That's over damped. Right. And then there's an under damped too. Those have to do with like electric circuits, like oscillations, electric circuits. But anyway, this is a response function for a bell. This is for a hook, like a Hookean elastic, and this is for a Newtonian fluid, and this is ours, which is exponential minus t over tau kind of decay response function, a simple relaxer. So that's kind of what that question's asking you to do. Then get 5 minutes. Explain the two-time correlation function. So that kind of was done by it's in that paper. There's another paper here. Let's see. There's another paper. This thing. This is by this Bicondoa. Right. So basically this goes through the entire correlation function thing. This is referenced in this paper. So that's linked, so basically you can kind of fish through this. Like this is a typical decay pattern where things get slower with time. So it's a curing system. This is where the two-time correlation function was invented. So you can glance at that. Hookean elastics. That's what I tried to do. So his equation 5, if you look at his second paper, he explains that this is the viscosity, this is the strain rate, and this is the stress, and they're modified for relaxation. This is a Newtonian fluid equation. It has nothing to do with Hookean elastic. And it has nothing to do with harmonic oscillator, it has nothing to do with exponential decay. It's just Newtonian fluid with these relaxation times stuffed into it. Right. So the question is like, what does it have to do with? It's basically just a Newtonian fluid equation. And he's modified for the time. And he explains that in the second paper where he brings up that equation. Figure 4 compares the mechanical amplitude. Let's see. All right, so figure 4. Let's see. I got 4 minutes. Enough time to go to figure 4. All right, figure 3. Figure 4. Oh yeah, so it's Newtonian here. I mean, it's Hookean here, Newtonian here, and this is at the relaxation point. That's what it's asking, isn't it? Figure 4 compares model, solid, yielding, liquid. Why are the plots star-shaped? So I kind of went through that. Why does the star center move? I went through that. That's got to do with this del thing, shift factor. It's going to a greater acquisition of non-recoverable strain. So that has got to do with his it's got to do with the del shifts. So basically you're going to get more loss in the thing if you go to higher shifts in the thing. Higher shifts in other words, this shifts more because you have more loss, which has to do with like the position you are on this curve. So the further out you are, you have less recoverable strain. and it's becoming more fluid-like. Hopefully that's all right. And then figure 5 shows the agreement between XPC and mechanical. This comparison develops normalized Helpful if this is larger. Let's see, PSN. Oh, then he says the reversible dynamics are therefore spatially confined to long-lived portions of the sample, and the recoverable strain in the nonlinear regime is manifestation of constrained positional fluctuations in the fumed silica particles. And that I don't know what it means. So basically, I think you gotta see what you can come up with for that, because this seems to be like the crux of his total statement of what's happening in this paper. But I'm not sure he has evidence for that. And the reversible dynamics are spatially confined to long-lived portions of the sample. So that means that he has a nonlinear regime has to constrain positional fluctuations of the fumed silica. So it means it's an inhomogeneous sample. So he's got, and I think this is pretty common when people resort to like they don't understand what's going on, that it's inhomogeneous. There's regions that are the recoverable strain, let's see, confined, the reversible dynamics, the reversible part, the fluid part is spatially confined to long-lived portions of the sample. I don't know what that means really. I think you should try to figure out what that means. That seems to be the crux of the paper, but I don't really get it exactly. It seems to be kind of confusing. Recoverable strain and the nonlinear, that's why I put it in there. I was like, I wanted to be able to understand it, but I haven't actually achieved that. So maybe you guys can figure it out. If not, don't worry about E. Like, just put something down and say like, because I still don't really understand exactly what he's saying there. First, anyway, we can try to figure it out. We're out of time. So when we put the, so email me if you got. So that, on Monday, we have Monday, Nichols is coming, right? So we've got like a mandatory or whatever.
So I just wanted to be sure that which books should I follow, particularly for qualifier exam, for polymer physics and advanced thermal. Like I have chemical advanced thermodynamics, and another one is this book. I'm just not sure are those enough, or I should bring other books also. This one, the physics of polymers.
Yeah. You looked at I have the old exams on the webpage,
Yeah.
Have you looked at those or?
Yeah.
Okay, so that's good. And try to answer those. And then, yeah, that's a good book to bring. I mean, what else? For the thermo, there's a book that we used in the class, right? For the thermo.
The fundamental of chemical
It's like,
advanced thermodynamics.
yeah. So you can't bring a PDF, huh?
Yeah, I have the PDF and I think I'll print. I have printed it.
Oh,
I'll show you.
it seems like kind of a waste.
Yeah, but
Yeah.
I didn't get the book from library.
Yeah, I didn't think of that.